Kyla, who is a PhD student here at UC Berkeley studying planetary science, where her work focuses on using computer simulations of planetary materials at extreme pressures and temperatures to understand the properties of planetary interiors. Nice short and sweet intro. Perhaps maybe you saw the cat that was there earlier. With that, please, Kyla, take it away. Very excited to hear your talk.
Thank you for coming out tonight. So first I was told the content level should be aimed at high schoolers. So if you have a PhD in astronomy and it feels like this talk is for high schoolers, you would be correct. But I still think that planetary science at any level is amazing. And so I hope in the next hour I can give you a crash course in planetary science, as well as give you an overview of particularly the interiors of our planets and work that's being done very much today to try and better understand the interiors of our planet, because there's still a lot of unknowns here. So again, I'm Kyla. I'm a third-year student in Earth and Planetary Science, so not astro. They do occasionally let me into this building. And I was also an undergrad here at Berkeley. I studied planetary science and chemistry. So if anyone has any questions about undergrad programs or anything like that, feel free to reach out, or any questions after my talk, feel free to email me. And so as a summary of what I'll talk about today, first we'll go through solar system and planetary formation, and then I'll spend a good bit of time walking you through our solar system. And then I will tell you a lot about high pressure research that's going on related to understanding planetary interiors. And then finally, if we have time, we can talk about exoplanets. So I think when we're trying to understand how planets form and what the planets in our solar system, what their interiors are, trying to understand the diversity that we see, it's really important first to just understand how solar systems form. If you like this image, I recommend this YouTube channel, Chris Gazat. All of their videos have this beautiful animation style. And so understanding solar system formation, I would say we should start with just an intro to stars. Again, I'm not a stellar astronomer, but stars essentially form when you have regions of hydrogen and helium that become sufficiently pressurized to start nuclear fusion. And so this is what produces light, what produces heat. And eventually stars will start synthesizing heavier elements, helium, carbon, oxygen, neon, etc. So the heaviest element synthesized in stars is iron. And then eventually stars will run out of fuel, they'll die, many of them will explode. And in this process, they'll spread the elements that they made, often far away from them, into space. And so you'll have these particles of dust and gas collecting into clouds. So a very famous example of one such cloud of interstellar gas and dust is called pillars of creation. And so I have shown here two pictures from different amazing telescopes. We have the Hubble and then James Webb. And so these are really optimized to take pictures of this feature with different wavelengths of light. And so these are called the pillars of creation because within these clouds, you have many new stars and solar systems being born. And so this process occurs when you have a big cloud, and eventually it becomes dense enough that it will gravitationally pull inwards on itself and become this large rotating sphere. And then after enough time, and when it becomes dense enough, it'll actually flatten down into a disk, and that disk will be rotating. And in this process, the gas through gravity is being pulled mostly to the center. And so this is how you get a new star forming, is all of the gas from this cloud got pulled to the center. And when it becomes dense enough, then it will become a star where nuclear fusion will start here. And so this is one artist's rendition of an early planetary disk. You can see the star forming in the middle, and you can see gas and dust spread throughout the disk. And so then this is an artist's rendition of later on in the planetary disk. So you can see that dust particles collide, they form pebbles. Pebbles collide, they form bigger rocks. And eventually you reach the point of having small, what we call planetesimals. And once we reach this stage of a planetary disk, planets grow actually not by accreting dust, but by growing and accreting more of these. Essentially the collisions of these mini planets. And this is how planets eventually grow to their final size. And so this is the process our solar system went through, eventually resulting in us having a solar system that looks like this. And so I will point out these sizes of the planets are to scale, the distances are not. If you want to see the distances to scale, it looks much more like this. So you'll note really close to the sun, we have all of our terrestrial planets and then Jupiter, and then all of the bigger planets are much more spread out. So when we look at these planets, you probably notice a huge distinction between the ones closest to the sun and the ones farther from the sun. Like the ones closest to the sun are so tiny compared to the ones farther out. And so these ones we call terrestrial, similar to Earth, and these ones we call Jovian, which is Latin for Jupiter-like. And so our terrestrial planets, in order of size, and also including the Moon, Earth, Venus, Mars, and Mercury. And so all of these have a similar structure, though different radial proportions of composition. So all of them have an iron core, and then they all have a mantle that's made of rock, like silicate melts, and then all of them have a crust, which is a less dense rock. And then this would be what we call our Jovian planets, which are really broken up into two different categories. So you have the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. So the gas giants, I should say, all of these do have a core of rock and iron. The gas giants are distinguished by having a huge amount of gas in them, so huge composition of hydrogen and helium. The ice giants instead have a really significant composition of what we call planetary ices, so water, methane, and ammonia. So then the question really becomes, why did we get this huge differentiation between the inner planets and the outer planets? And it really has to do with early solar system temperatures, as well as the freezing points of various molecules that existed in the early solar system. And so around 4.5 astronomical units, an astronomical unit is the distance between Earth and the sun, we have the frost line for water. And so essentially, clearly, if you're right next to the sun, it's very hot. And as you go farther from the sun, the ambient temperature decreases. And as you pass a certain point, water will freeze. So to the left of this line, you would have water as a gas. At this pressure, you wouldn't have a liquid phase. And to the right of this line, water is an ice. And so we talked about how planets grow by picking up dust and how this dust will collide into pebbles. So when you're in the inner solar system, you cannot pick up water, ammonia, methane as solids because they're gases. But in the outer part of the solar system, they're now pebbles of ice. And so the planets, as they're growing, are able to pick up not just pebbles of rock, but also pebbles of ice. And so they're able to get much bigger solid cores. And then because you have much bigger solid cores, you're able to gravitationally attract much more gas as well. And so Jupiter and Saturn are much closer to this frost line, which meant they were able to pick up a lot more of the ice. They were able to attract a lot more of the gas, which is why you see they're still so big compared to Uranus and Neptune. Uranus and Neptune picked up a lot of ice, but not as much gas because Jupiter and Saturn were gobbling it all up, which is why they're mostly ice. Okay, so now that I've explained this major difference between the inner and outer solar system planets, I thought I should give you a brief walkthrough of our solar system, starting with our sun. So as we already talked about, a star is primarily a ball of hydrogen and helium in which nuclear fusion is happening, which causes heat to be emitted. Our sun is quite large compared to Earth. You could fit 13 million Earths within the sun, which I always find to be a really impressive number. And then we already discussed the difference between the Earth and the sun is called 1 astronomical unit. And that's equivalent to about 92 million miles. So at this distance, it takes 8 minutes for light from the sun to reach the Earth. And so our sun has become bigger and hotter over time, and it will continue to do so. And in about 5 to 10 billion years, it will run out of fuel, it will become very large, and eventually it will cast off all of its products of fusion, and it will become a white dwarf. And so just a couple of interesting solar features that you're likely to see, especially if you try observing a total solar eclipse, for example. A solar flare is when you get a huge protrusion of plasma from the surface, which is related to fluctuations in the magnetic energy. And you're also likely to see sunspots, which are when you get these dark spots on the surface of the sun, which is also caused by fluctuations in the magnetic energy. But here it's because these regions are actually cooler than the surrounding surface. Okay, now to planets. I'm going to skip over a few briefly because I think that to properly appreciate the uniqueness of the other planets, it would be good to review what's unique about the Earth. So I'll go through a few things that make Earth special. Foremost, I think, is that Earth is the only planet we know of that has life. There's a huge amount of research being done to try and find life in other planets' moons or detect signatures of life in atmospheres of other planets. But as far as we've been able to tell so far, Earth is the only planet with life. Suspiciously, Earth is also the only planet we're aware of that has water on the surface. And so here I really like this graphic that shows proportions of really the rocky underlayer versus the volume of water and air. I think so much of our experience with the planet has to do with the atmosphere, hydrological cycles, but realistically, most of the planet is a big rock. And so the correlation between water and life is because water is really fundamental to biological processes. But it turns out that Earth is the only planet that has water because we exist in this perfect distance from the sun, which is called the Goldilocks zone or the habitable zone. So again, as we talked about, if you're too close to the sun, it's very hot. And if you're too far from the sun, it's very cold. And there's this perfect region around the sun where water can exist as a liquid. And so Earth is the only planet in our solar system, this correlates to our star, that is within the habitable zone. But of course, our sun has changed in brightness and luminosity over time. So we're aware that Mars also used to be in the habitable zone because Mars used to have liquid water. Earth is also special because it's the biggest terrestrial planet and the only one with a moon, which is also not a coincidence. It's accepted that Earth's moon formed from a giant impact with another smaller planet. Essentially what happened is this planet impacted, the entirety of this planet, which is dubbed Theia, disintegrated along with a significant amount of the original Earth. And then this debris collated back into a sphere with a big debris or disk of debris around it, which eventually coalesced into the moon. I thought you might enjoy seeing a video of this happening from some smooth particle hydrodynamic simulations. If it will play. Do you have any idea how to make this work? Sorry. Sorry, this worked at home. Okay. You can envision what I was talking about. I encourage you to go look up this video later. It's very cool and they give a lot more details than I do. Another thing that's interesting about Earth is that we have a liquid iron outer core. This is not unique amongst the planets, but it is what generates our magnetic field. So essentially, our planet is broken up into crust, mantle, liquid iron outer core, and solid iron inner core. And so having this liquid component means that we have convection. So this is the inner part, which contains most of the heat. This is the outer part, which is liquid. So when the liquid touches the inner part, it gets hot, which makes it rise. And then around the mantle, it starts getting cold, which makes it drop. So it's convecting in these circular cells. And this is also a conducting material. And so this process generates our planet's magnetic field, which protects the planet from harmful solar radiation, except at 2 points where the magnetic field exits the planet and enters the planet, which gives rise to beautiful auroras in those locations. So it's where charged particles are hitting the atmosphere at the poles or near the poles that you get aurora australis and aurora borealis. So our moon is geologically dead. It has no atmosphere, it's internally cold, and it's geologically dead, which is why we have so many craters on it. So in the early history of the solar system, before all the planetary debris cleared, there were a lot of giant impacts, including on Earth. But Earth has tectonics, Earth has weather, so all of these craters have been washed away, except for a few, like one in Arizona, the one from the asteroid that killed the dinosaurs is still under the Gulf of Mexico, but for the most part, we can't see them. But the moon has no mechanism to resurface its surface, which is why you can still see them. And so by geologically dead, I mean there's no interior or surface processes which change the planet, which drive heat flow, which produce magnetic fields. And so people often liken the moon to Mercury. They look quite similar. Similarly, they don't have any surface processes, so they have very cratered surfaces. And here's a comparison of the size of Mercury to the moon and to Earth. So it's much closer to the size of our moon. So we already talked about the surface. There's no surface geological activity. There's no atmosphere on Mercury at all. So a lot of people have said for a long time that Mercury is geologically dead, which is not true because Mercury still also has a dipolar magnetic field, just like Earth does. So this means that Mercury still has a liquid iron core convecting in the same way that Earth's core is, driving the same magnetic field. A lot of people still said, okay, but it's still mostly dead. But then last year, there was some pretty interesting news that if you watch Mercury's surface closely enough, you're starting to see additional wrinkles develop. And this is because Mercury is cooling on the inside, as all planets are. And as it cools, the planet is contracting, which is actually causing some buckling of the surface. And so you can start to see additional wrinkles form. Another really interesting thing about Mercury, since I promised to tell you about their interiors, Mercury has a giant iron core compared to the other planets. You can see radially, it's the vast majority of the radius. And so this is because iron is magnetic, the sun has a strong magnetic field, and so as the planets were forming and there's iron spread throughout the planetary disk, the magnetic field from the sun is pulling iron inwards. And so this region, quite near to the sun, where Mercury was forming, had an abnormal amount of iron, giving rise to its very large iron core. Okay, jumping into Venus, here's a comparison with Earth, very similar size, and of course, it's right next to us. So in many ways, Venus is a sister planet. So then why does Venus look like this and Earth looks like this? Well, that's because Venus has a brutally hot sulfuric acid atmosphere. So this was a picture taken by a Russian lander, and the Russians just kept sending them, and they just kept melting. So no one has sent a lander to Venus in over 40 years, because between the heat and the sulfuric acid, the landers all stopped working almost immediately after just sending a few pictures back. So this is one of the very rare pictures ever taken there. So the surface of Venus looks very much like a desert. And the reason that Venus ended up this way is because of a runaway greenhouse effect. So it's thought that at one point Venus was quite like Earth with oceans and potentially even life, but then Venus is closer to the sun. And so that means it gets extrasolar radiation. And so it becomes hotter, and then the oceans start to evaporate. And this isn't often talked about, but water is a really fundamental greenhouse gas. And so as you start having huge amounts of water in the atmosphere, it becomes a runaway greenhouse effect. And eventually all of the oceans boil off. And then eventually all of the oceans, or I should say the water now in the atmosphere, escapes the atmosphere, leaving just largely carbon dioxide. Venus is also interesting because it's very similar to Earth, but as far as we can tell, never had tectonic plates. Venus also has no magnetic field, meaning that there's no convection going on. So either it has a liquid inner core, but there's not sufficient impetus for it to start convecting, or it means that it has a solid inner core. So this is still an open question. And to give you some more big news, Venus still has active volcanoes, which was a popular news article last year. It's actually kind of a funny story because the story was that, Venus doesn't get landers anymore, but there's still orbiters of Venus quite often. And so one of the orbiters had collected surface data, like topology, and no one had really looked at it that carefully. And 20 years later, someone revisits it and is able to see within a short time frame, they're able to see topographical changes. Like they're able to see the landscape evolving, meaning that they actually were able to capture on video, essentially, a volcanic eruption. So this is still pretty cool because being able to actually observe volcanism on other planets, I think is amazing. Okay, Mars, I think you're probably all familiar with. It's our other neighboring planet and planet most likely to be able to foster human life. It's quite small compared to Earth. And here you can see its signature ice caps. So these are carbon dioxide and water ice on the caps. And modern Mars is very windy, very dusty, very cold. So the average temperature is negative 81 Fahrenheit. On Earth, the average temperature is 57 Fahrenheit. Mars also is the opposite of Venus. It has a super thin atmosphere, meaning that it has no intrinsic greenhouse effects to enable it to support liquid water anymore. I already showed you the ice caps. But we know that ancient Mars had a huge amount of liquid water because mapping the surface, you see a number of basins that were obviously lakes that were thought to have persisted for many millions of years. There's evidence of riverbeds, there's evidence of deltas. So a delta is where a river meets a bigger body of water and it slows down and drops a huge amount of sediment. There's also evidence of sedimentary rocks that form from flowing water. And so this means that ancient Mars at one point had an atmosphere that could sustain liquid water. And it's just that now, or at some point, Mars lost its atmosphere and it no longer has the pressure to sustain liquid water. So a couple of years ago, you probably remember, NASA launched Perseverance to Mars. And Perseverance is hanging out at a delta because they think that deltas are an area of a lot of sedimentation, is an area you're most likely to find signs of life. And the really special thing about Perseverance is it's drilling out a number of cores of various rocks. And strangely, it's just kind of dropping them all over Mars. And at some point, the European Space Agency is going to design another rover to come collect them and bring them home. And so each of these samples is about the size of a piece of chalk. And I think it'll probably be 15 or 20 years before they're brought back. But then we'll learn so much about Mars and its history from all the different chemical analyses that can be done on these samples. So another open question about the interiors, it's really not known if Mars has a liquid core or a mix of a liquid and solid core. Mars also does not have a magnetic field, which means it has no convection. So this is a really open question. And then more, this kind of like science in action. You see scientists learning things and arguing with each other and ideas evolving. So in 2021, it was said, oh, we see that Mars has a really large iron core. And then they came back a few years later and said, actually, we don't think Mars has an anomalously large iron core. After all, we think that the iron core of Mars is for some reason surrounded by a liquid silicate melt. And so our measurements made us think this was an iron core. So you see, there's still a lot of open questions, even about the terrestrial planets that we can put rovers on and do seismology on. So that's pretty amazing. Ancient Mars also had a lot of geological activity. So it has Valles Marineris, which is the biggest canyon in the solar system. We talked about how Mercury was starting to wrinkle. So this is actually a big wrinkle from Mars cooling. It's 20 times wider, 5 times deeper, and 10 times longer than the Grand Canyon. Mars also has the biggest volcano in the solar system, though it's no longer active. So this is twice as tall as Mount Everest. And so because Mars is much smaller than the Earth, it has much less gravity, meaning that this mountain was able to grow a lot larger before the force was able to pull it down or prevent it from growing any taller. So next to Mars, past the frost line, we have Jupiter. And I included this picture because I want to show you Jupiter also has auroras, because Jupiter also has the same dipolar magnetic fields that Earth does. And of course, Jupiter is enormous compared to Earth. You can fit 1,300 Earths inside Jupiter, and Jupiter is 300 times more massive. And we've already largely discussed the interior of Jupiter. It has the core, which is rocky and iron, and the exterior is a hydrogen-helium atmosphere. But because it's so big, the interior reaches these extreme temperatures and pressures, something like 25,000 Kelvin and 100 million atmospheres. And so when you reach these extreme pressures and temperatures, you start getting really exotic phases of matter. So in this case, Jupiter and Saturn both have huge interiors of what's called metallic hydrogen, which has been not verifiably synthesized on Earth. But which predictions of this and computational work on this excellently match measurements of the properties of these planets. This is also work from a few years ago from my research advisor, if any of you know Professor Melitzer. He's also a faculty member here in Astro. So he did work showing that near the top of the planet, hydrogen and helium actually become immiscible, meaning that they do not like to mix, and you will actually have helium rain down into the deeper parts of the planet. Jupiter's current moon count is 95. Probably the four you'll be most familiar with are the Galilean moons. So these are, of course, the ones that Galileo could observe with his 17th century telescope. And these moons are all really amazing and unique. So Io is the most volcanic surface in the solar system, such that NASA and European Space Agency are afraid to get their orbiters too close to it. Europa it has a really icy crust and then a subsurface salty ocean. So a lot of exobiologists, maybe astrobiologists, think this could be an excellent breeding ground for life, maybe even hiding there and we just can't tell. Ganymede is the largest moon in the solar system, and Callisto has the oldest surface. And of course, Jupiter's most famous feature is its giant red spot. So there's actually a cyclone that's been going on for at least 400 years, because Galileo was able to observe this, even with his 17th century telescopes. Saturn is the most distant planet that can be seen with the naked eye. And again, Saturn is gigantic compared to Earth. And Saturn's internal structure is very similar to that of Jupiter, just slightly different ratios, like radial relationships of the different layers. And Saturn, I would say, is most famous for its rings. Though actually all four of the giant planets have rings, just not all of them, I think, are visible with like the typical visible spectrum. Some of them are only visible with UV or maybe IR. I'm not an astronomer. But interestingly, the rings are very young features, like maybe 100 million years old, which does not sound young, but when you consider the planets are 4.5 billion years old, the rings are very young compared to the moons. And so 2023 big news, before 2023, Jupiter was thought to have the most moons. That's kind of a competition these two planets have, constantly going back and forth. But in 2023, it was announced that 50 plus new moons of Saturn were found, bringing the total up to 146. And one particular moon is really fascinating, which is Titan, which is the only other body in the solar system that has a stable liquid on the surface. However, Titan is very cold, so that liquid is not water. That liquid is a hydrocarbon, which is very interesting. So we can finally get to my favorite planets, Uranus and Neptune. They are both blue because they have methane in the atmosphere. And we see they are still quite large compared to Earth, but not nearly so much as Jupiter and Saturn. And to be honest with you, these planets are the farthest out. They're very enigmatic because they've been really not at all visited by spacecraft. Each one has been visited by a single spacecraft doing a flyby, which means Voyager 2 passed by Uranus for about 16 hours and Neptune for about 36. And that's all the spacecraft data humanity has on these planets. So there's a lot of open questions. And I'm now going to tell you my biggest pet peeve, which is that people think these planets are cold because they're called the ice giants. And I understand why they're called the ice giants. That's because they're primarily composed of what planetary scientists call planetary ices. So water, methane, ammonia, carbon dioxide, hydrogen sulfide, we talked about farthest out in the solar system, they become ices and they can become accreted. And so, but now these planets reach, 500 GPa in the core, 10,000 to 15,000 Kelvin. So these planets do not exist as cold solids except on their very outermost surface. In reality, under really extreme pressures and temperatures, you get really unique compositions and phases occurring in these planets. One popular theory and something that I work on is that these planets have a large core of superionic material. So this is when you have light nuclei, like protons, diffusing like a liquid, where the heavy ions are still fixed in a stable lattice position. And so this is a really interesting phase because it's very ionically conducting. And so people try to liken it to the magnetic fields of these planets. So I just went through their interior structure, but just a review. They do have an iron rocky core. And then the most common model is they have huge mantles of ices. This is actually becoming more controversial in, I say, modern planetary science. Because nearby planetary bodies, like the moons of these planets and Pluto, have an ice to rock ratio of more of 1:1, versus this model is more like 20 ice to 1 rock. And so there's really no explanation for how these planets would be able to form with so much ice. But this is based on fitting density profiles. So these are the planets I primarily study for my research. So very exciting to say that it's very likely that the next big NASA mission, what they call their flagships, will be an orbiter and probe to Uranus. It doesn't have a name yet, so people are calling it UOP. So an orbiter orbits the planet for as long as it has battery life for, essentially. The probe is a one-time use deep into the atmosphere and then deep into the planet, and it will collect compositional and pressure and temperature data until it falls too deep and melts and loses connection. But it will still give us invaluable information. So this is definitely all of the planets in the solar system, right? We're not missing any? None of you are nostalgic for one?
Pluto is kind of a planet, but not really, right?
Yeah, so those of us that are older than 2006 feel bad about Pluto. Unfortunately, Pluto was demoted in 2006, and I'll tell you why, but first I need you to understand the asteroids that are exist in our solar system. So just some verbiage. An asteroid is just a small rocky body that also orbits the sun. And I say small in relation to planets and dwarf planets. Like Vesta is the largest asteroid, and I think I can't read this, something like 300 miles across. So this is in distinction from comets. Comets are made of rock, but also ices, which means that as they start to heat up, the ice melts and they start losing debris. And then as they get hot from the sun, they'll have a gas tail. And so when you see something having tails like this is a comet, not an asteroid. And then finally, meteorites are when bits of asteroid break off and actually make it through our atmosphere to the surface. And we call meteors this bright tail that you see as a bit of asteroid is hitting the atmosphere and attempting to make it to the surface. And so our solar system has 3 big zones of asteroids. So the first one is this one. It's between Mars and Jupiter. The second one is outside of the orbit of Neptune, which we call the Kuiper Belt. And the third one is actually a giant sphere surrounding our entire solar system, which is called the Oort cloud. And so Pluto actually lives in the Kuiper Belt. And so, but Pluto is not the only thing that lives in the Kuiper Belt. It is not the only even large thing that lives in the Kuiper Belt. And so you see that these 4 are also dwarf planets in the Kuiper Belt. So Ceres actually lives in the asteroid belt between Jupiter and Mars. And so it turns out if you count everything kind of planet-like in any of the asteroid belts, we would have over 200 planets. And this started to become an issue for astronomers because that's a little bit unreasonable. And so astronomers came up with 3 rules that bodies had to meet to qualify as a planet. The first one is they have to orbit the sun. So clearly Pluto does that. They also have to be massive enough that they become spherical. And clearly Pluto also does that. Versus compared to some of the other dwarf planets I was showing you, not necessarily the case. And so the third one, and the reason Pluto got disqualified, is that it has to clear the neighborhood around its orbit. And what that means is it can't be passing through a region that's full of rocks, it's full of asteroids, and needs to be large enough that it's either flinging things out of its way or it's gravitationally attracting them towards and growing with those things. And Pluto does not do that, and neither do any of the other dwarf planets. And so as a result, Pluto was demoted and is now a dwarf planet. And that's a gif of New Horizons passing by. So, but that said, Pluto is still fascinating. It is a very tiny planet. And Pluto's moon is very, very large compared to the size of Pluto, when we're talking about like planet-moon relationships in our solar system. So Pluto has a pretty dead interior. It's solid iron, but then it also has, the crust is a thick crust of ice with a subsurface ocean. The ice being nitrogen ice with some like water ice mountains, which is fascinating. It has a very thin atmosphere. And so my favorite fact about Pluto is it has a roughly 250-year orbit around the sun, which means that since it was discovered, it has not completed a single orbit around the sun, which I think is a little bit mind-blowing. Okay, so now I told you a lot about planets, I told you a lot about their interiors and a lot of open questions here. So then you might be wondering, how do we actually know what planets are like on the inside, being that we cannot directly observe any of it? So a popular thing when you can actually touch something onto a surface is seismology. So this is essentially tracking how sound waves pass through material. Do they pass through, the speed at which they pass through, how they bounce, and based on this, you're able to come up with a map of what the interior of a planet looks like, and get some sense of what the material is if you know what the kind of properties of propagating sound of that material is. So obviously this is done times a million for Earth. We have seismometers all over the planet. It's also been done for the moon. It has been done recently for Mars. And I think that's it. And a lot of the planets you just cannot touch. Like the giant planets have such thick atmospheres that if there is a solid surface down there, it is at way too high temperatures for any human instrumentation to possibly survive. So then this is kind of a recipe for how you would imagine a planetary interior if you can't touch it. So you can watch the planet and its orbital interactions with its moon and its sun, and so you can estimate the mass. And then just by looking at it, you can estimate the radius, and so then you can get a bulk density. And with that and some intuition as to what each layer should be, you can come up with a density versus radial profile. So here 0 means the very core, 1 means the very surface. Now when you have discontinuities, that means you're having a compositional change. Like this would be an iron core, this would be a gaseous envelope, etc. And so then you ask the question, what materials would have this density, especially at the pressure and temperature you expect here? And obviously it's a lot more complicated and iterative than I'm going into here, but really this is highly dependent on understanding the properties of planetary materials at extreme pressures and temperatures, which is really what I do for research, which I think is fascinating. So you can either study planetary materials at extreme conditions experimentally or computationally. So I use computers. A lot of people do experimental work, and it's amazing when you can do collaborative work and find the same results. So I'll walk you through some really cool experimental techniques. So you can do what's called static compression, which is where you're very slowly compressing things, or you compress it and let it sit for a while. And the most popular way to do this is using what's called a diamond anvil cell. Again, diamond is the hardest material known to man, so usually it will not break if you're trying to pressurize other things. And so in between two very tiny diamonds, you put a very, very small sample of whatever you're trying to study in a gasket, and then you turn some screws, and the pressure increases. And then using various instrumentation, you can heat the sample up, or you can probe it with x-rays to try and determine what structure is in there. And again, this is to show you how tiny these apparatus are. So the other popular experimental way of studying materials at high energy conditions is shock compression. So really using giant lasers. And so this is a simulation that I ran, but I thought just so you could see really what's happening to the material when you shoot a giant laser at it. Lasers hit the surface with so much energy, they will what we call ablate material. So they'll like push material off the other direction, which creates a shock wave through the direction you're trying to go. And so the usual recipe here, take a material, shock it with a giant laser, use a suite of instruments, to try and determine what pressure temperature condition you wound up at. Hopefully it's of interest to the interior planets. And obviously, I'm way oversimplifying this. There's a whole suite of experimental tools to try and optimize what pressure and temperature you end up at. And then you can use what we call X-ray diffraction. So shoot X-rays through the material, collect the light that results, the pattern that emerges will tell you about the crystal structure. If there's no coherent pattern, then that means that the material was melted. And so some of the facilities that do things like this, very close to here, we have SLAC. And SLAC does not have any super high power lasers, but they're becoming known for having instrumentation that has kind of amazing, like they can take extremely precise measurements, which is surprisingly hard when you're trying to shock things to, you know, 1 billion atmosphere and tens of thousands of Kelvin. And so this is cool because this is just in the hills in Palo Alto, and it's actually a 1 mile long beam line. So the second biggest, strongest laser in the country is the Omega laser at the Lab for Laser Energetics in Rochester. And so this laser, I think, has roughly 60 individual lasers that are then all collated on this kind of target chamber. And this is a picture I took of the target chamber when I got to visit. So for scale, these are handrails that are like this tall. And each of these black circles you see here must be like that big. So this is a very, very large instrument. And all of these lasers are directed at a single point, which is like the head of a pin in size. So that's what's required to be able to reach these planetary interior conditions. And of course, everyone's favorite laser would be the NIF. This is the strongest laser in the world, which is right over the hill in Livermore. And so this is the giant facility, like warehouse-sized facility that houses it. And here's a schematic. And I'll point you to these 2 laser bays. Each of these hold 96 individual lasers. So you have 192 lasers being collated into one target bay. Here's what it looks like inside these laser bays. So each of these individual lines has its own laser. And this is what the target chamber looks like from the outside and from the inside. And so then this shows how all of the lasers are then collated to hit the single target. So again, this orange sphere here is the size of like the head of a pin. So it's absolutely incredible technology. And it was this laser and this team that was able to achieve nuclear fusion for the first time about 1.5 years ago. Not nuclear fusion, what they call ignition. So fusion that is self-sustained. And so when this is actually realized on a large proportion, this will be just incredible for our energy production. And if you're Star Trek fans, Star Trek 2013 filmed inside the NIF, which is amazing when you find out that most scientists that work with this laser are never allowed in this room. Like we have laser technicians and the actual scientists don't get to go in here and play with things. Okay, so then what I actually do, which is my favorite part of all of this, is I do computational work to study materials at high pressure. And so all over the world, we have these gigantic computing facilities. We have one of the best ones in the world right up the hill, Berkeley National Labs. It's called Chrome Letter. I'm sure most of you know some Chrome Letter. Physics faculty here that won a Nobel Prize, at least the Astro. Anyway, so as you can see, these cute computers are the size of auditoriums. They're applied to study questions about climate, drug design, and also planetary science if you can talk them into giving you computer time. Another one of the best ones in the world is here at Livermore National Lab. And so they're really all over the world. They can be a little bit hard to get time on, but once you do, you can do amazing things with the computational resources. And then you might be wondering like what your simulations actually look like. So I took 3 of them that I've done recently. And so this one is the one I showed you of a shock simulation. And so essentially what many of these look like is you put together a box of atoms or molecules at the pressure that you want, of the composition that you want, and then you study how the material evolves over time. Or you can Just do like static calculations to see like what is the energy, can we compare what the most stable compounds are, but obviously the dynamic simulations are more fun. And so then this is a video of crystallization. So you can see at this temperature and pressure, the ions prefer to be in a solid lattice. The green is showing that they're adopting the crystal formation of the solid. And then I already told you about superionic materials. So here you can see I've tagged just a couple of protons and I'm tracking their trajectories through the cell. So note that the blue and the red ones are not diffusing, but you see the protons diffusing throughout. And so this is a really amazing phase of matter. If you're familiar with like lithium ion batteries, solid state batteries, so those have lithium superionic as the charge carriers. Okay, so we do have time for exoplanets. So this is a screenshot from last year. Maybe I should back up. Exoplanets are planets outside of our solar system. And I think nowadays we're a little bit spoiled with thinking like, of course, there's planets outside our solar system. The first exoplanet was discovered 5 years before I was born. So if we were here, 33 years ago, then a planetary scientist would be saying we have no proof that there are planets outside our solar system. So, let's not forget this is an amazing advancement in planetary science in the lifetime of a young person. So this is from last year. This number is now around 5,600. You're seeing a very large throughput annually. And NASA does have this website if you want to go check out the current statistics. And so this is a cumulative number of exoplanets discovered per year. You see what I'm talking about? In the early 90s, there were none. It looks like the first one was discovered around like 1996. Oh yeah, that was the year I was born. Okay, so the year I was born was the first exoplanet was discovered. And so you can see it's really an exponential growth over time, but you do see significant jumps from, for example, the introduction of new technology. Like I believe this jump was associated with the introduction of the TESS space telescope, whose exclusive mission is to look for transiting exoplanets. And so of the 5,000 plus that have been found, I want to make the distinction that what has been found is not necessarily representative of what exists. It's representative of what our detection methods are able to find. So for example, small planets that are very close to their star, very hard to find. Large planets that are very far from their star, also pretty hard to find. Most planets have been found by transits, which I'll discuss in a minute, and transits rely on the same object passing in front of its star multiple times. And so this results in something that's big enough to actually make a difference in the amount of light that we see, but also close enough that it can pass by the star multiple times in the amount of time that we can look at it. But so overwhelmingly, most of the exoplanets we found are in this range called super Earths and sub-Neptunes. And we don't have one of these planets in our solar system. So it's unclear, like some of them might be large terrestrial planets. Some of them might be what we call water worlds, which have a really huge like surface ocean all over the planet. And some of them might be mini ice giants. And we also have found a number of gas giants, including interestingly a number of what are called hot Jupiters. So Jupiter-like planets that are much closer to their host star than our Jupiter is. So there are really, I think, three popular detection methods. The first one is transit, like I already kind of explained. So when a planet will pass in front of its host star, the amount of light that we see from that star dips while it's in front of the star. And so if we can see this cycle of dipping and then coming back multiple times, then we can verify that a planet is passing in front of it. And overwhelmingly, the vast majority of exoplanets that have been found by this method. Doppler imaging is a more classical method, but it's also much more expensive. And so the idea is that, a planet orbiting a star, we say a planet orbits a star, but realistically, they'll orbit a mutual center of mass. And so when a planet passes by, the star itself will wiggle a little bit. And so if it's wiggling away from you, it looks bluer. No, it looks redder. And if it's coming towards you, it looks bluer. See all the astrophysicists in the front row nodding. And so based on this, you're able to determine that something is perturbing the orbit of the star. and there must be a planet there. And then finally, a much more, okay, that YouTube video doesn't want to play either. A much more modern detection method, which really only works for very large planets far away from their star, is direct imaging. So this means like actually taking pictures or videos of them. So this requires like a lensing technique that blocks light from the sun or like from the host star so that you can only see the surrounding planets. And so for example, here, this is where the star would be, but it's blocked, and so you can see the light from the planet that's circulating around it. All right, so I actually finished a bit early, so thank you so much for your attention, and let me know if you have any questions.